Okay, so this talk is about a thing that I thought was like a sort of trivial observation, and the more I looked at it, the more interesting it got. So it's basically, the gist of this talk is that lenses, which I'm going to introduce, because you don't know there, are a very special case of continuation passing style, which is a way of writing functional programs. And I'm going to try and define everything I mean by that. So what's a lens? So there's a nice animation, the Bruno made, where you think of a lens. It's kind of like a way of, the name is meant to indicate that you're focusing on part of the data structure, and then you're going to change something, and then you're going to get back to some other changed data structure. And they're surprisingly old in various forms, but the form I'm going to talk about here is the so-called bimorphic lenses. So let's say we start with some type S, the source, and then we reduce that to some A, which doesn't stand very good. And that's like sometimes called the get part. So this reduces the problem. We start with something, which is our big database. We take a view on it, so we get an A. Somehow, this A turns into a B. This is the kind of the update. And then this goes back to make a T. So this is source and target. And the other part is that the backwards part gets access to the original source. So you kind of think of this as we take a view, our databases, it's like taking a view, and we do an update to the view, and then we get back to the original databases. So it's a general way of doing that. And the kind of point I want to get across here is that what again is doing is waiting for this sort of part here to be joined up, right? So sitting there, what we really want to do is get from S to T. That's our goal. And what we're missing is something that goes from A to B. So there's sort of, at some point in the future, there'll be something that bridges this gap to get us back. So we can sort of try and write this down as a different way of writing down a function, right? We're just sort of want to get from S to T, and we need an A to B. So we can write this down as we start with S, this is the Haskell type. Then given something that will get us from A to B, we get a T, right? So it's kind of a simple way of writing down this type, except that the things that live in this type are considerably more expressive than the things up here, right? So and the point is that this one, we produce one A, and then it gets transmuted to a B, and then we come back and we get a T. Here, we start with our S, and then somehow the thing that implements this function is allowed to use this continuation, the A to B, as many times as it likes. There's many different ways as it likes, as many ways to produce a T. And what I'm going to try and convince you is that lenses are essentially one-shot continuation passing style. Continuations are multi-shot, and there's a whole lot of things that in between. Okay, so that's the outline. Right, so we need a common framework for these things to live in if we're going to compare them. So I'm just saying, just for clarity's sake, the traditional continuations, we have a fixed answer type, R. So this sort of takes the continuation and then produces somehow an R. And continuation passing style is a style of writing functional programs where we never return anything, we always call the continuation. So we're also going to call this. But now I'm going to use a kind of more general thing where the two answer types can vary, which fits in with this part of the lens diagram. So people looked at this kind of generalization of continuations and realized that it has something of the structure of a monad. So if we define a type like this, I'm going to sort of change about what the letters are. So we have this kind of continuation monad, except for we don't have one answer type, we have two answer types. One is for the kind of the interim, and one is for the final. And we can also write lenses as, so what I'm going to do here is factor out this original S. That means I get to reuse it as this S. I get to reuse the lens. So a lens, it returns an A paired with a function from S to R. Right, so that's the step here. So across the bottom. Okay. And what do these have in common? Well, they're both what's called parameterized monads. So they're monads where we can't always do a bind operation, we can't always do the sequencing, but we can do it if these parts join up. What does that mean? So we have a return that's, so I'm just going to write this as M for the specific zero F1. All right, so for any A, we get a return. So for a normal monad, we remove these parts. But here, we get there's two parameters, and they have to be the same. So this is like the skip rule in Hall or something like that. It's just pre-states and post-states. And then there's a bind, which I'll do in Pascal thing. So we have an MRSA.
Sick.
And we have, and taking the A, we have an MSTD. Yeah, I managed to do all of that without writing the word staff anyway. Then we join up, so notice here the two S's match. So this is we do the first one, we go from R to S, we do the second one, we go from S to T. So altogether, we go from R to T. Right, this is parameterized. And so there's many other instances of parameterized monads. You can actually make place the pre and the post state. Is a good example. And the interesting thing is that both of these do support both of these operations, right? So the lens one in particular is a return. What we do, it takes the A, it's there, and then because both of these are the same, we can have the identity function. For the bind, we take the A and we use that to get the second one.
Stand on the other side of the board.
We take the A, the first one, because we can just pop it out. That'll get us the second one, so then we can produce the B at the end. And then we compose the two function parts. And once you look there, it looks a bit like this famous chain rule combination of identity transition. Another interesting thing is that the lens one is essentially because you think parameterized monads are to monads as categories are to monoids, in the sense that monoid is something where you can always compose. Category is something that imposes some kind of typeness. So now we have this typeness, and we have to make this S match up in the middle. And this is sort of the analog of the writer monad, but for parameterized monads. We take the category of the ambient category we're using as the things we're writing. We have to join up. So that suggests a sort of generalization of this, where we could have A cross and then some other category SR, right, and have it still work. Anything where we can compose things. Okay. But these are, we don't just put any parameterized monads, these are going to have some kind of other operation. And these operations are selected to make the rest of the talk work. So the first one is called feedback. And this is inspired by this kind of view of this is a kind of writing thing. What we're going to do is we're going to write a morphism to the trace that's being collected. So for any function from S to R, we'll get RS and then the unit. Okay, so this sort of adds a kind of bit of feedback into our limits. So we're kind of in this thing, we're kind of doing something in this part. So normally we're programming in forward part. That's just what we're doing with return bind. Very so often we can sort of drop that backwards into the feedback operation. And then the other one is called run. Think of this as an operation which generates things in the monad. Run allows us to observe things. What do you do when you have a monad? It's the same thing you do when you have a burning building. Run. Yeah, so we've got an R, but we've managed to close this gap. So they're both the same. Then we can plug in the identity, right? So if these two are the same, then our SSF, then we get out an R again. This allows us to sort of close the feedback loop, close the feedback loop. So I'm going to say that any kind of step operator that takes 3 parameters, yeah.
Let's just ask what feedback does. I didn't quite understand. Is it just like the backwards stuff?
Yeah. So feedback for lenses. F is unit F. Right, so it takes the F and plugs it into here, and then just puts unit here. Feedback for the continuation. Well, it takes the current continuation, okay, and that's from A to S. A is going to be unit here. Here. So we just need to post compose with that. So it's sort of what it does is it adds something to the continuation.
Is there any parameterized potential from which is two kinds of negation?
That's a good question.
It was interesting when a continuation gets post-composed.
Yes. Yeah, so this is something that we do. Yeah, so you can think of the continuation is what happens next, and now we're adding something to after that. That's what lenses do, right? So the continuation is this bit. Adding feedback is adding something to go into this part. So I'm going to say that there's a 3-place type operator which supports these 4 operations. So return the bind, close monad, and feedback in the run, plus 6 axioms, so 7 axioms. So the first 3 axioms are the analog of the monad laws for parameterized monads. They formally look the same. The other ones are that feedback preserves identities of composition. What does that mean? That means that feedback of ID must be equal to just return unit, and feedback of F followed by feedback of G is whichever way around makes the types right. Right, so that sort of makes sense that if we do 2 feedbacks one after the other, that's the same as applying the composer's feedbacks. And then ones that involve run are if we do a run of feedback F followed by return A, then that should be equal to just applying F to A. Right, so if we go straight here and do an A, and then our feedback, and these 2 types are the same, and our feedback is this, and running it should just close the loop. Right, so this is quite a strong law.
So the semicolon here is the non-necessary.
Yes, so sorry, semicolon is when A is unit, then yeah, it's just
Not the same semicolon. Oh, that's the same.
yes. And then final law, which is a little bit weird, is if we have two computations and we run the second one, return its value, and then do it after the first one, and then run the whole thing, that's the same as running through the first one. I mean, if we've got C1, we bind for a day, and then we return, run C2A. So we run the second one. We're running, do C1, get its value, and then we run the second one, and then run the whole thing. That's the same thing as just run C1 bind. Right, so if you think about what run does, it kind of closes the loop. If we close the loop twice, but we do that as a kind of the final thing, it doesn't matter if we just this is a sort of non-obvious one that came up in proofs. If you know anything about delimited continuations, then one thing to keep in mind is that run is basically reset. This allows us to generate a new scope. Delimited continuations are a sort of programming language tool where you can sort of grab segments of the stack, treat them as first class. That's what's going on there. Reset says cut off the stack here, and when I do a grab, this is how far it goes. And then the more powerful one of feedback is what's called shift, which allows us access to the context. And basically just allows you to inject any thing which uses the whole monad. Use that all power. So this allows you to just say, give me the current continuation like you are. So the shift and run or shift and reset give you a kind of form of limited applications. Here we've got run and feedback, which is very limited kind of. Okay, so altogether, I'm going to call these things that support these four axioms plus the three from parameterized monads a feedback monad. And also, I'm going to make a category of these things. So the objects are going to be these feedback monads, and the morphisms are going to be just natural transformations. So, in functional programming terms, polymorphic function from the first one to the second one for all R, S, and A, such that it preserves all of these operations. Kind of obvious. You write down equations. So we get a category of feedback monads, and the interesting thing is that continuations will be the terminal object in this category, and lenses will be the initial object. So what does that mean? That means that for lenses, so L is initial. That means for any other feedback monad, there is a morphism from L to M. And it's unique. And that morphism is, and we call it out. So it goes from L, R, S, A to M, R, S, A. So the only thing we know about M is it has return and bind and run and feedback. But we know that L is precisely a pair of an A and S. For R, we get A and F. And what do you do? Feedback F. So Okay, just because you've got a kind of canonical form for every kind of simple feedback. The other one is that C is final. So for the M, there's an M to C. All right, and just by process of elimination, I'm going to have to use run to make this correct, because I'm used to that. So I'm going to call this in, goes from M RSA, C RSA. This takes an M, and then we run. Take the continuation, and then we run the result of doing M, DNA, and then returning the continuation by the And it's possible to prove from the axioms I showed before that again, this is unique morphism into C. So we have a category of these kind of feedback impacts where lenses are initial and continuations are terminal.
We don't need any two sets for one category.
So
Why is it one category, not national?
because it's not approximation.
Between one and one. You don't need them because it's categories of national.
The different natural transformations, I can't think of an obvious two cells to have that would be useful.
So it is strictly not binary.
Yes, oh, yeah. Okay, so we've got kind of story now where lenses and continuations fit into the same framework. And I've tried to tell you there's a kind of intuitive idea that lenses are kind of exactly one-shot continuations. Somehow the program can use its continuation once. And the continuation passing style are multi-shot, they can, or arbitrary shot continuations. This function can use an A to S as many times as that. So what lies in between these two? What kind of useful feedback modes are there which aren't lenses or continuations? So the intuition is that lenses use their continuation exactly once. The obvious thing to do is to relax that. Right? So either we could have at most once, or we could have finitely many times, or n times. So let's try and what happens if we use it at most once. So in that sense, we'll go back to this diagram. We've either got an S and it produces an N, and then that has to be a continuation to get back to a T. Or it doesn't use a continuation, but we still have to produce a T, so it goes directly to the rest of the T. How are we going to encode that? So let's go ahead and lead lens. So again, we're going to have the reusing case that goes, we return an A and then we're waiting for an S and we get back to an R, or you immediately return an R, you immediately give back the answer. How about one where we're allowed to use the continuation a finite number of times, but we're allowed to choose how many times we use it. So this one we use it arbitrarily many times, remember? But let's say we're going to use it a finite number of times. And a finite state number. That's what isn't it? So now we're going to say there exists a natural number. We're going to produce n many inputs for the continuation. We're going to get back n many intermediate results. And then we're going to have to stick them all together to get back our final result. We're going to have A to the n, and then S to the n. Right, so we produce n many results. Our kind of collaborators at the other end take n many A's, give us back n many S's, and we have to stick them back together to get them on. So you can see here, this is different kinds of data access. This is one that could fail. So we have to have some way of saying, okay, I'm going to get to some substructure which is in A, but it might not be there. In that case, I'll have to produce the default value for the final answer. But if it is there, I need to update it, and I'll use that as my final value. Here, there are some number of substructures, which you don't know yet. So we find them all. There's n of them, and we produce, our collaborator produces n answers from these fictional original things. So this is like, so we find everyone in the database who was doing CS316. There's n of them, and then we update them all with past knowledge, and we produce that, and you can use code. Okay, and we can sort of stitch both of these together into one class of examples. I see we can also state this one as this kind of sigma thing where we have a Boolean saying whether or not the value existed. And with a horrendous use of notation, I'm going to say this Boolean is either 0 or 1. And we'll see the definition of it. Right, so now let's see what's the difference between these two. This one, we get a number of answers. This one, we get 0 or 1. Okay. Okay, so what's the general pattern? So, I'm sure a lot of people are thinking in a moment, hey, this is a container. So what's going on here is that these are shapes of the container, right? So what we're doing is we've got some type of that describe the shape of the output, but without actually telling us what the output is. This tells us what the shape is. The shape is it has n elements. This one says the element this has 0, 1 elements. Shape is
Oh, I was going to ask a question later, but I see we're going in a slightly different direction. I was going to ask whether these are affine traversal and traversal.
yes, sorry, yeah, yes. So if you know about lenses, these are affine traversals, or I should say,
I don't know if I spoiled the.
no. I suppose it's something I haven't had to make clear. To get lenses right, it's chopped off the source. Right, to get lenses, it's really a function from the source into this tab in the C. Right, so it's actually
Flies the arrows.
where's the arrows? So it's like in this thing, it's T B thing. And in fact, there's applies the arrow constructions, applies the category construction for parameterized monads, which will give you precisely the usual category of lenses, or what's now being called lenses. So this is what's actually going on. This is the source, and then for one of these feedback monads, this is the final result, this is the intermediate result, and this is the other intermediate result. So the data flow goes, we go from S to A to B. And yes, if you're familiar with the Haskell lens library, then these are affine traversals and these are traversals. And these distances. Right. So I can say what a kind of general method for making these is. So if we have a set big S of shapes, and we have a family, S-indexed family of sets of positions. This is for this one, it's going to be Booleans, and this one is going to be naturals. And in positions, if we're given a natural, this is going to be the set of all numbers less than that, so the set of all indexes into that list. And if it's Boolean, then I'll just do the one. So we've got Booleans as the S, and then if it's true, then it's the unit set, it's false, it's the empty set. Okay, so this tends to be where it's set the unit type. So we're going to need a bit more structure than this. And what we're going to need it to be is a monad in the category of a monoid in the category of Cartesian container morphisms. I'll explain what that means. So a container morphism between two of these things are called containers because we think of them as this is the shape of the data structure, and then this is the set of positions, and we think of it containing that by saying that a function from positions to points. And so yeah, lists are natural numbers and products. And if we have SP to S prime B prime, then a container morphism is a function F from S to S prime, R takes a shape and then goes backwards. So not uncoincidentally looks like instances, right? We have a function that goes from shapes to future shapes, and then a function that goes backwards in positions. This is actually how we're mapping the shapes forward. We have to map positions backwards. And then a Cartesian one of these, Cartesian is not a great name, but there's reasons for it. This is an isomorphism. Right, so it says the shapes, we can change the shape, but positions have to be isomorphic. Not allowed to, we can rearrange them, but we're not allowed to throw any away or anything. Now, what's the thing we need for this? Well, what we need to be able to do in order to find a bind and a return of this monad, we need to have enough structure to be able to say what's a kind of one shape, and if we've got a shape and then a shape for every position in that shape, we just glue them together. So this is what's actually going to be a monoid in the category of these things. And I'll just spell out monoid with respect to the composition. What this is going to be, we're going to have a unit. It's going to go from 1 to S. That's going to pick out our one shape. So both of these examples, this is really this natural numbers, it just goes to 1. This is the natural numbers, so it begins. And we have a backwards one. In this case, it will witness the fact that the unit star is isomorphic to 1. Right, so we need to know that the number of positions for the one shape is given. And we also need join. A bit more complex. So if we have a shape and then a family of shapes, and they have positions, and this allows us to take two shapes morally and turn it into one shape. But the second shape may be parameterized on the positions in the first shape. Join, this one's complicated, that's from plus 2. This way. Isomorphic sort of carrier shape. So you can read that. So basically what the join does is it takes the pair of shapes, the second one is parameterized with the first one, and squashes it down to one shape. So if you think this is a natural number, then for every one of the every kind of slot in that natural number, there's another one. And what does this do? Well, it adds them all up. This is just a generalized sum operation.
Yeah. So if you're Peter Hancock, you think of shapes as commands, and positions as responses.
Yes.
And what you're saying here is that your command response language allows sequential programming.
Yes.
Yes, so we have a command, and then given a response, we get another command, and we can put that all together to make one command.
And the response is the pair of the responses.
Yes. Yeah. And importantly, this is an isomorphism, so we can always go back from a pair of responses to a one response. That's not usually how. This is what makes this a bit stronger. So examples of this are list and maybe. And then a lot of other examples look a bit like this, maybe, because it's a really strong kind of thing. So, for instance, you can't have anything which collapses positions because it violates this isomorphism thing. Right, go back to feedback monad. So if we have this S&P, we can define an LSP RSA, and this changes to a T. For any shape, we produce PS many A's. This is the equivalent of this A to the N here. And then given PS many T's, we get an R back at the end. And for any one of these Cartesian monad-like things, we get another feedback monad, another kind of lens. And this includes this example, both of these examples, and several others. So you can, for instance, you can structure the shape like a tree. And as long as you can arrange your plugging operation, that you can work out where it came from in order to get the joint to be an isomorphism. Okay, so we get this, and then not only do we get that, we get an operation for this monad to go with the feedback and the run, like the feedback. For any S, you get kind of top S, which, and for any R, right, so we get another operation that we can do with this monad. So right, think of this as kind of a primitive operation. The imperative language of writing these lenses, that we tell it what shape we want. It's like, aha, I've discovered that there are n elements.
Yeah.
That gives us, okay, someone's asked for element 5, and we do that. And then the feedback, we have to put back, we get told what the original element was, and then send it back to.
Again, the command response metaphor is perhaps well, it's a clear fit here. It's you're issuing a command,
Yeah.
You're getting a response, and you know what you're going to do with the response to get.
And yeah, it's going to turn that feedback into
Yes.
kind of shared response. Right. And I just want to finish up with something that doesn't work, but I think is revealing, which is it doesn't work for boring foundational reasons. Okay, so we get a whole kind of load of examples of these feedback monads, one for every one of these things. But we can't get continuations, right? Because we can't get this arbitrary arity. The arity is the size of the set, right? But if we were allowed to let S itself be set and P to be the identity, then we would recover continuations. Because we would have, in that case, L set ID R SA would be there exists a set, as well as use some parametrises. I claim by parametricity that you can like, collapse out this S and you'll get back the continuations thing by substituting this. Right, so if it weren't for the fact this is entirely inconsistent by sort of saying that a set is a set in a set, this allows you to sort of say that somehow continuations are kind of the limit of the process, right? We allow the error keys to get arbitrarily large. I don't say what the process is, but if we allow the error keys to get arbitrarily large, then we recover continuations as kind of limit.
Is there some, like if I fix the parameters like R and S and choose some continuation in that case, can I, like, is it the case that every continuation for fixed
No, so I think the problem is that even with fixed RNS,
so fixed
this
A,
as a function on A,
oh,
it doesn't have a rank.
I see.
And that's the kind of the problem. So my conjecture is that every one of the feedback models which has a rank with respect to this.
Oh, I see.
Probably has a representation as an S and everything.
Yes, it seems to, I guess,
Yeah. So that's kind of why I think it's true. So it basically means that as long as you use your continuation a fixed number of times or limited number of times, fixed by some polynomial, then there'll be representations of this. I think. So I think that's everything. So yeah, so in summary, even from a practical programming point of view, you no longer have to write this 1.3 nonsense with lenses. You can use do notation and the feedback operation. I didn't really emphasize that, but you don't have to write compose lenses anymore. You can just write do notation and operations to talk about lenses. But also, lenses neatly fit into a family that reaches all the way up to continuation passing style in a nice way. One thing that's kind of intriguing is, well, does this work for dependent lenses or things like this? So this is a bit like lenses, right? You go forward and you go back. And if you make S family over A, you can sort of make that work. So I haven't worked out what that is as a kind of monad-like thing. It's not a relative monad. So somehow it takes pairs of, well, it takes containers sets. Something which has this shape. So it takes a set, and then also takes a pair of sets. You can make a lot of the sort of formally work out. So you can define a return and bind, and then you can sort of get the containers as a Kleisner category for this.
So I was saying the thing in the middle there is fam set.
Yeah.
What if it were pow set?
This is how
It's just SRO set. Sorry, pow set is set error set.
oh,
Well, it's choice of an S. No.
Instead of some S, instead
Yeah,
it's product.
yeah. So I mean, fam set is choosing some sets we like as the image of a function, and pow set is choosing some sets we like by saying what evidence would convince us that we like that set.
yeah.
It's always, and then that begins to smell of predicate transformers, which of course
Yeah.
these things ought to be.
Yes,
It should be doing weakest precondition.
there comes this, and I'm going to rearrange it to the center.
Yeah.
And continuation, right? That line continuation button. Okay, that's putting out. Sorry, take nothing else away from this. Lenses are just funny kind of monad.